All right, welcome there, calculus folks. Today's stuff is a shorter lesson, but it's the intro to 3 days of the same types of problems and fairly intense problems, but you can kind of see how it was coming. This was kind of something that was coming. Optimization problems is a big fancy title, but the idea is we want to find the best, that the optimal solution. So here's the general idea. Hopefully you've got this in front of you. The problem is to find the independent value that gives you the best, which might mean the minimum or maximum dependent value, whatever x and y might be, and we'll see lots of examples. So the solution, we draw a diagram if possible. It might not be possible. We want to find a formula, whatever that formula will be, and that will depend on what type of problem we're dealing with in the next few days. It says, then, after we've got a formula, we need to substitute, rearrange, or otherwise fiddle, and that's a rest-all copyright math term there, fiddle, with it until you have one independent and one dependent value, dependent variable. So for instance, we might have, and we will, volume equals length times width times height because it's some sort of box. But, if we take the derivative of this, which one are we taking the derivative with respect to? We've got one output variable v and three input variables, so this is no good. We need to substitute, rearrange, or otherwise fiddle with that until we've got a y equals a function of x sort of situation going on. And that will be the big task for us, actually. It says apply the extreme value algorithm to find the mins and maxes. And that was last class. Last class was the idea we find the derivative when it's zero, right? When the derivative is zero, that's when we get an extreme value. And then we check the endpoints and be mindful of the domain of the function that you define. So between the derivative and the endpoints and the domain restrictions, we'll be able to find the maximum and minimum values of a function in a certain area. So the GRASS technique is something that maybe you haven't seen since grade 9, but certainly we'll see in the next few days that it'll become a useful tool to get us going. This idea of, what's given in the question, what's given, what's required to answer it. A is the analysis or planning step. S is actually the solution, and S is the statement for us to remember to write our closing sentences. And we're going to see in the next few days, this is almost like a setup video here. The problem types, ones that were given the function, and that's the ones that we're talking about today. I'm going to do one, teeny little example, a baby example, and then just set you off on doing some homework. But it can, if you're given the function, it could be in all these different avenues of society, physics, business, biology, whatever. I think the first one that we do is in physics, actually, a science question. And then we'll do a day where we talk about measurement, and there's these classic problem types, the farmer and the fence, the best box, distance and time, the two ships passing in the night, and the economics and science, the greed problem. All these we'll see in the next few days. For now, we're gonna start with the given the function. So here we go. So the example is from time t with t between 0 and 5, a particle moves horizontally according to that function. So it's moving back and forth according to this function, where we think of right being positive, left being negative, etc., all those things that we talked about. So this is kind of a nice review of the last day's motion stuff. So it says find the min and maximum distances over the time interval. So to find the minimum max distances, well, what's the first step is to calculate s prime. Well, s prime at t, I just take the derivative, no problem, and plus 21. Hopefully that derivative's right, and then I set that to 0, right? Because minimums and maximums happen when the derivative is 0. So then I got negative 3t squared plus 2t plus 21 equals 0. I'm going to multiply everything by -1, and I don't know, does this factor? Does this factor? I'm not sure. Sorry about that there, folks. I had to pause for the cause. Probably you didn't know the difference, but where were we? We were um, factoring this. Numbers that multiply to get, well, -63 and add to get -2 eventually. Or you could break down the middle. However you like to factor this. This is going to be 3t minus 7 and t plus 3. There's the -21, -7 and +9. -7 and +9, that's wrong, so I need to change the signs. There we go. So -21, there's +7 and -9, and yep, good. Factored correctly. You could use the formula, right? Even some of you have your quad solver, which you can go ahead and use that, I suppose, too. A little bit cheatsy, but I suppose you could. And so then we get those are our two spots where the derivative is equal to 0. So then we check the endpoints, right? The first step was to set the derivative equal to 0, and then we check those values. Oh, hang on. P was supposed to be between 0 and 5, so we don't have to use the -1. We have 3. We have the endpoints 0 and 5. And so then we can calculate the minimum and maximum values when t equals 3. Remember, we substitute back into our original distance, not here. Remember, this is the velocity function. We don't want to find the maximum velocity until the next question. I got to go find my calculator. All right, bam, there's my calculator. I've actually done some calculations. So S at 3 was 48. S at 0 is easy peasy. It's just 0, right? T is 0, S is 0, starts at the origin. And then when S was 5, or T was 5 rather, bang, there it is. So there's my maximum, there's my minimum. So a maximum distance of 48 meters, I think. Doesn't say units. Occurs when time equals 3 and a min distance of 10 units, 0 units. Let's tidy that up, shall we? It occurs when t equals 0. So not that much different or more difficult than what we learned last day. B, find the minimum maximum velocity. So minimum and maximum velocity. So B, the velocity function, is just this first derivative, right? It's -3t squared, what's the rest? Plus 2t plus 21. The maximum and minimum velocity occurs when its derivative is 0. So that means I should calculate that derivative. That goes down plus 2. And notice this is actually the acceleration function, right? So the maximum or minimum velocity occurs when the acceleration is equal to 0. And this is always the steps we follow for our min-max thing. This is kind of like the first step. And so we got 0 equals negative, what is it? T equals positive 1/3, I believe. Great. And so then that's the only spot, so I'm going to check. Now, what goes here? So I know 1/3's here, and 0 and 5, because those are my endpoints. I have to check. What goes here? Well, what am I investigating? I want to find the minimum and maximum velocity. So I'm going to investigate the velocity. I have to substitute back into here. For A, we are investigating the distance or the position, but here it's the velocity. So no problem. Bing that into a calculator, bing, 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 and you get 21 and a third, trust me. 0, you get 21. 5, bing, 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 you get negative 44. And so notice, what do we got? We got a maximum velocity here, and then a minimum here. So maximum velocity occurs at when the derivative is 0. So a max velocity of 21 units per unit, probably meters per second, but it didn't say, occurs at time equals 1/3. A min happens at the end point, right? Minimum velocity of negative 44 units per unit occurs at t equals 5. Just a little bit of strangeness here. One could argue that this is the maximum velocity because it's the highest number of these three, right? So just because we're traveling at 44 units per second or meters per second, and we're going left, because remember that's what that meant, isn't that the maximum velocity? Then would this be the minimum velocity? Well, we're not too worried about that. Certainly between 21 and 44, there's going to be a 0 in there somewhere as well, right? A 0 velocity, and we had that up here, right? When the derivative was 0, we had a 0 velocity at t equals 3, for instance. What we usually say is the maximum number. We don't care about which direction. So the maximum is the highest velocity right, and the minimum would be the highest velocity left. We don't care about the bigness of the number. We're interested in maximums and minimums being right for positive, left for negative. Okay, so don't get that goofed up. There's a bunch of different ones in the textbook, and you pick your faves and give them a go. These questions get much more interesting in the videos coming up.